Hey everyone. Today's example should be pretty straightforward, but I really like it. It's in fact an example of a homework that a slight derivative of a homework I've been teaching for a number of years, and I've been doing that because I think it's actually so important. What we're going to be doing is grid search. We won't be implementing it from the ground up like I often encourage in one of my classes, but instead we'll be using the Scikit-Learn function, which makes it a lot easier. Makes it maybe a little more confusing to understand if you haven't used it before. But the nice part about this feature is everything just basically works, so it doesn't require a lot of hand holding. In fact, it may almost work so well that you wonder how we ever got along without it. But it is true. You know, this work goes back to our cross-validated grid searches that we used to do in the mid-2010s, really focused on the idea that we were looking for the best both hyperparameters that would help us, and that's what we'll look at in the first example, but then the best classifier in connection with the best hyperparameters, which is what we'll look at in the second example. So let's just get started. We're going to be using logistic regression as our first example for a classifier, and I chose this really because the C parameter, the regularization parameter in logistic regression, is really quite crucial. You have to get it right. So it's a good example to get up and running. And then we're going to be doing two things. We're going to be using the grid search that's cross-validated, and we're going to be using the test train split. These are just very regularly, easy to use and regularly used tools. So if you haven't seen them, you should check it out. And finally, for our data sets, we're actually going to make a classification data set just to make things very straightforward for our first example. So we're going to get X and Y from our classification data set. We'll have a number of samples, which is equal to 1,000, and a number of features, which is equal to 10. And if we look at this, x.shape, we see that in fact that's what we have. We have 1,000 rows of data, each with 10 features. We'll use a test train split train test split to separate it out and to double check. We'll do the same thing again, and we'll see that we have 750 rows of data with 10 features, which is what we would expect. Note that I didn't provide the parameter of how large the test train split should be. That defaults to 0.25 if you provide no other parameters. And next, what we're going to have is we're going to really kind of the guts of this is we're going to have a parameter grid. These are the combinations of features that we're going to be considering, the hyperparameters we're going to be thinking about. So we'll take for each value in our first entry, that's C. Notice that this is a dictionary where the keys are the parameter names and the values are lists of potential values. So 0.001, 0.01, 0.1, etc. And each of these will be paired with one of the L1 or the L2 penalties. So when we run this model, we're not training a single logistic regression. We're actually training a large combination. And on top of that, we're using cross-validation. So it's a large number of classification runs. Once we have this in place, what we'll do is we'll make an instance of that CLF for the logistic regression, just like we typically would. And now, instead of just training with our normal CLF.fit, we're going to create a new variable, which is our grid search. And our grid search takes in the CLF that we're working with, logistic regression. It takes in the parameters that we're interested in, and takes the number of cross validations we're interested in this case 5. And now, instead of running that CLF.fit, we're going to run grid search.fit over the X train and Y train. And when we run that, we see that we get a result quite quickly. And now to test or inspect how well our model's done, we use the grid search and we'll look at a couple of different variables. One is the best parameters and the second is the best score. And these show us that in fact, the best parameters were a C value of 0.01, a penalty of an L2, and the score, the accuracy in this case, is 0.92. So quite useful on its own. This is a nice encapsulated, no nonsense example that you can train from, but this isn't necessarily how I would use things. This is really only geared towards one classifier at a time. I wanted to show you an example that did a better job, I think, of showing you not just a single hyperparameter sweep on a classifier, but how I would use it, which is to test multiple different classifiers and then run multiple hyperparameter sweeps. So we're going to start with importing additionally random forest because it's easy. It's often the algorithm that works the best on this sort of spreadsheet type data. Pull in a Gaussian naive Bayes. And this time for a data set, rather than working with that fake data from up above, we're going to use the breast cancer data from Scikit-Learn. And then I'm doing something here. I'm suppressing all warnings. Now, this is not something I'd recommend that you do in your production code. This is something that I'm doing simply because it makes a less cluttered screen to look at what we've been working on. So again, this is just for teaching. I'll load my data and overwrite what we're looking at. I'll clear this for a minute. Let's pull in our X train and our Y train and test, and you can see that we're splitting everything up. We're using a test size of 0.2 this time. No real reason we have to use that. We could use a test size of 0.1. Again, depends on what, the size that we're working with in terms of what our data is. And I'm interested to see exactly what our size is, because if we don't know, it's about 455 examples divided over 30 columns of data. So 30 features, 455 examples. That's what we're going to pass in. Now, this is where things start to get interesting. We're first going to take a classification list of all of the different types of classification we'll be performing: logistic regression, random forest, and naive Bayes. Now, this is a list of classifiers, and you'll note that typically when we call one of our functions, we'll put parentheses at the end. That's not what we're doing. We're calling just pointers, or the functions themselves. We haven't made an instance of them. So now we will make an instance of them down below, but right now we just want pointers to the original functions. Next, we need to have hyperparameter sweeps that correspond to each of our example codes. So this is the hyperparameter sweep related to naive Bayes. This is hyperparameter sweep related to random forest. And you'll see that I'll create another list of these hyperparameters: logistic regression, which was defined up above. Note that these are in the same order, of course: logistic regression, random forest, naive Bayes. And now what I have is a scenario where I can pair each entry, each value in the CLF and each value in the parameters one by one, and I will have the right parameters and the right algorithms. Not rocket science. Finally, I'll start with our results, and this is really where the code is going to perform something that's useful. Let's bring these in. We'll start with an empty list of results, and we'll capture everything that we're interested in here. And we're going to use this enumerate function, which I use quite regularly. We'll enumerate over the CLFs. So for each classifier, for each type of classifier that we're interested in, we'll get an index that's 0, 1, 2, and the actual classifier: the logistic regression, the random forest, and the naive Bayes model. And the reason we'll need this classifier is in a moment, we're going to pull out the 0th, 1st, and 2nd parameter. So it's a nice way of sort of working to pull out pairs of values. First, the value that you're interested in, the actual classifier, and then the index, IDC, the counter, to give you the position that we'll use for parameters. So we have a classifier. Again, that's this pointer to this object. We will now make an instance of it, and we'll now use exactly as we did above, the grid search to pass in that CLF. And then we'll use the hyperparameters that correspond to logistic regression, and we'll run that 5 times. So we're redoing right now in the first pass, on this first pass on the loop, what we did above. And we'll do an X train and a Y train for the search. And then we're going to append the pointer to the type of algorithm that we're looking at, and the best parameters for each of those algorithms and the best score. So now, instead of just doing it for logistic regression in one run, we're going to run first logistic regression, then random forest. So logistic regression has finished already, and it'll take another second or two for random forest to complete. And then finally, we'll get naive Bayes, which should come almost immediately. And the reason you might see some of that delay is that we have 3 different features that we're looking at the comparisons between. We're now not looking at just the interactions between number of estimators and max depth. We're actually doing a 3-way comparison, so that increases the space that we're assessing quite dramatically. So now we can look at our results, and let's just move this to the top. We see, in fact, as is not too much of a surprise, that logistic regression gives us this 0.953. Random forest pushes us to 0.958, and naive Bayes gets us to 0.94. And there's not much of a difference here, but random forest does trump the others by a small margin. And so what I'm going to do is I'm going to take my results. I'll take the example of this classifier. That's the Scikit-Learn model. And we could have written this so that we look to the highest value and then use that highest value to pass in here, but I just hard-coded it. So we'll take an example of that random forest classifier. We're going to make an instance of it, as you can see here. And what are we going to do? We're going to pass in the parameters for the optimal model. So we've recognized that random forest is our optimal model. We're going to pull out these parameters, which you see here, and we are going to create a CLF. Now that we have that CLF, we're going to fit on the X train and Y train. Now we're fitting on all of the data that's available. We're not running cross-validation. We're at the final stage of really testing to see. We want to represent the statistic that we're going to present, our stakeholder who's interested in. And now we can run that CLF.score, and we get a value of 0.97. So actually, our random forest exceeded the test train split when we were doing our grid search, which was only 0.95. We actually did a little bit better in the holdout set. So I really like this example, primarily because it provides, first of all, at least once a year, I'll do something along these lines, especially when my clients don't know me very well and they're looking to make sure that I am doing something rigorous. I'm not just sort of telling them what the best answer is. I'm actually going and investigating it. Just in these, 50 lines of code, but really it's even shorter if we were to remove the first pass in 25 or 30, we have run a wide selection of different algorithms. 3 is non-trivial, and then the number of hyperparameter comparisons. We've trained a huge volume. Each of those has been compared one against each other. We've decided upon the optimal decision, and look, it's not much effort. So, 10 or 15 years ago, this would have been a really significant task and taken up considerable resources. As you can see now, grid search makes it really quite trivial. We're still doing a grid search. That is, there's nothing that's optimized about to decrease looking in spaces that we think aren't going to be successful, like we do when we use some of the AutoML tools. But for these kinds of models on scale of data that we're dealing with now, it's really not necessary in my mind. You can get things up and running quite quickly and have some real value. So my hope is that this will provide some value for your capstones or your end of semester projects, because I think these really are quite useful and really can move you forward quite quickly. Speak soon.